So this is question 16b from the 2016 HSC Maths paper. It says some yabbies are introduced into a small dam, and that equation there tells you the population, okay, where t measures time in months. So first question just says show that the rate of growth is given by that expression there. Now rate of growth just means a derivative, so we just need to differentiate what they've given us. So first thing I'm going to do is I'm going to rewrite their equation with a negative power for the bottom of the fraction, as we normally do. Okay, now what does this negative one do when I differentiate it? It's going to jump down, making everything go negative, and it's going to become negative 2. Okay, but then I have to use a chain rule and multiply by the derivative of the inside, which is negative 9.5 e to the negative 0.5t. Now that has to use a little chain rule in there as well. Okay. Alright, now notice the negatives will cancel. 200 times 9.5 is 1900, and so I'm left with this expression here, which thankfully does rewrite as I take the negative power to the bottom again into the expression we are after, so that's good. Alright, second part says find the range of the function y justifying your answer. So normally when we want to find range, we have some idea of what the function looks like. We normally have a graph or something, okay, and we look at what the y values are going to be. But this time we don't have that, and it looks quite complicated, right? But what we do have though is the gradient, is the derivative from the previous part. Okay, so that's going to help us a fair bit here. What you want to notice with this, okay, is that the top number is an exponential. So 1900 e to the negative 0.5t, and so it's an exponential which is never going to go to 0, never going to go negative. Okay, it's always positive. Okay, and same with the bottom. Bottom's always positive as well. We're even squaring it just to be sure. Okay, so if both of those things are positive, that means that the derivative, the gradient, is also positive for all t. It's always going to be positive. Okay, which means it's always going to be increasing. We call that monotonic increasing sometimes, okay, but that's very useful to know though, okay, that the function's always going to be increasing. Okay, now why is that? Because, well, if we calculate the starting value, okay, so when t equals 0, like how many yabbies were there at the very beginning? So as t equals 0, what's going to happen is that we look at our equation, we replace the t with a 0, okay, and so you see how in that term t's become 0. Okay, now of course e to the 0 is just 1. Okay, and so we calculate that quickly and we get 10. And what that tells you is that there were 10 yabbies at the start. Okay, and because it's always increasing, that means that the number of yabbies, the range of the function, it must be bigger than or equal to 10. That's what it means. Okay, but now the only question left is, does it keep increasing and boundlessly forever? So if I wait long enough, are there going to be like 3 billion yabbies? What happens to that number? Does it keep increasing and goes on and on and on forever? Or does it sort of flatten out and stop somewhere? Okay, and so to work that out, we have to see, well, what happens as t gets very, very big? If I wait really, really long, what's going to happen? Okay, so as t goes to infinity, what's going to happen is that that e term is going to have a very, very, very big negative power. And when I raise e to a very big negative power, okay, it's going to go to 0. Okay, use a graph of e or something, refresh yourself on that if you need to, but if I raise e to a very big negative number, it's going to go to 0. Okay, and so what we're going to get is that this actually goes to 200. So no, it's not going to boundlessly increase. Okay, but it's going to stop, or not going to stop increasing, it's not going to stop increasing, but it's not going to get past 200. Okay, it's going to keep crawling towards 200, but it's never going to get there. So what that tells you is that, well, the range now is that 10 is less than or equal to y. Really important that there's an equal there because we started at 10, and so we did get 10. Okay, but it's never going to go beyond 200. So less than, not equal to 200. That's really important. Okay. Alright, so third part says show that the rate of growth of the size of the population can be rewritten as this thing here. Now the rate of growth again is just the derivative, is just dy dt. But now we did calculate that back in part 1. okay, but we can't move with that, we can't go anywhere with that, okay? So the best way to do these questions is to start from that expression y over 400, 200 minus y, because we can work with that. Now how do we work with that? Well, we sub in their given expression for y, okay? And so if we plug that in, it's going to get messy, but we're going to do it, okay? We're going to do it, and that's what's going to happen. Alright, simplify what we can first. 200 over 400 is a half. Okay, now we want to do that fraction addition inside there, okay? So I know we sometimes forget those, but we take the 200 and we want to give it that common denominator. So I'm going to hit it with that denominator and we're going to do the fraction addition. Okay, now biggest thing with these is don't freak out at the mess, just work through it. Okay, we now expand that bracket that I've got in orange there, and we get this thing here. One more thing we can simplify, the 200s can cancel. Okay, and so that leaves us with this. Okay, and now we can just multiply those two fractions together. Okay, notice that 3,800 divided by 2 is 1,900, and so we simply get this. Okay, but now if we look back at part 1, that was the derivative, and so we're done. Okay, so this one, nothing too special, we just sub in y, and it's a huge algebraic mess, but just work through it and it should come out if we're careful with all the negatives and all the multiplying fractions, well, no, multiplying and adding fractions really. It should work out though. Okay, alright, part 4, find the size of the population when it is growing at its fastest rate. Okay, now when it's growing at its fastest rate means we want this dy dt, we want this rate of change to be as big as possible. We want to maximize dy dt. Okay, so of course we're going to use what we just got, that dy dt is this thing, much simpler than the expression we got in part 1. Okay, so we want to maximize this thing, and now at this point we could say, oh, it's this, we can expand it here and use some calculus and we can maximize that the normal way. But let's try another way. It's shorter and it's a bit nicer. Okay, we first see that because it's a sort of y minus y squared kind of thing, it's a parabola. Okay, the negative y squared means it's an upside down parabola. Okay, and now if we look back on the first line, okay, the expression they gave us dy dt equals y over 400, 200 minus y, well you see that that's factorized already. Okay, so you can read off horizontal intercepts, okay, as 0 from that one. Okay, and from the other factor, 200. Okay, and so we've got intercepts 0 and 200. The upside down parabola must look a bit like this then, which means it's maximized halfway between those two at 100. And so the population is growing fastest when y equals 100. Okay, now of course you can use calculus to work out the same thing. Okay, differentiate that, you'll get the same answer. Yeah, but I think it's just good for us to see and understand some parabola stuff again. Okay, and so that's the end of that question, end of that paper as well. So thanks for watching. See you later.